past 2 years have seen the prevalence of remote work rapidly rise to unprecedented levels. However, as circumstances change, many employers and employees alike are now left to wonder about its future. In this year's problem, we sought to clarify and predict the future of remote work. First, we estimated the proportion of jobs that would be remote ready in the next 5 years. Then we considered whether an individual worker would want to and would actually be allowed to work remotely. Thirdly, we synthesized our previous models to predict the future of jobs that will actually be done remotely. We ultimately ranked and quantified the relative impacts that working from home will have on each city. To start, we made the following 5 assumptions as displayed here, but we just want to focus on numbers 4 and 5. The percentage of employees in a specific industry whose jobs are remote workable is independent of the city they work in. We made this assumption under the thought that someone working a job in one location would share the same requirements in another location, and therefore the remote workability would maintain. We also assumed that the workforce of each city is the sum of the number of people working in the industries provided by the D1 city employment data spreadsheet provided for the challenge. This works because the spreadsheet has an other category that covered niche industries, and therefore all people were accounted for. We first projected the total number of employees in each industry for each given city in 2024 and 2027. Then summed the products of what we found with the theoretical percentages of remote jobs for each industry. We calculated the theoretical remote worker percentages based off of the following equation. Percent remote ready equals the sum of remote ready employees of each industry divided by the total number of employees of each industry. To calculate the numerator N alpha, we multiplied the total number of employees of each industry times that industry's theoretical percentage of remote workers, which we found from a white paper from the University of Chicago.
The hardest challenge of this question was dealing with a lack of data. This consequently raised the question of overfitting. To see this, we can look at the graph displayed, which is the average monthly number of employees in the greater Seattle area, one of the select cities that we modeled for. It can be seen that the data is quite choppy, and as a result, it did not make sense to fit the data to different industries to higher ordered polynomials, as this would most definitely overfit the data. So as a result, we chose to fit the data linearly. And we recognize that this means our projections are merely estimates, but allowed us to quickly estimate future employee populations for question number 2. Additionally, we think it's quite fitting as employment numbers are often related to population growth, which typically looks linear on a short-term timescale. Here is an example of the data we have on the theoretical maximum percentage of workers who can go remote in each industry. Together with our linear model, we now have all the pieces necessary to make the final predictions. By multiplying the percentages on the previous slide with our projection of each industry's growth, we arrive at the final predicted percentage of remote workable jobs in each given city. And our data concludes that the fraction of remote workable jobs in each city does not change significantly from year to year, which is most likely due to the short time frame that we are looking at. By taking into account multiple drastically different industries, we strengthen our estimations as more industries are being accounted for. Additionally, our model is quite flexible, as we can easily apply to any city as long as we know the composition of workers in each industry for that city. And if needed, we can easily modify any variables and come up with new results. And our sensitivity analysis shows the adaptability of our model, as we are able to adjust our variables by plus or minus 10% without any extreme changes. However, our model is still based off of linear growth, meaning it will not adapt to more complex scenarios such as rapidly changing industries or long periods of time. This is a significant downside to our model since industries in the real world are more likely to experience exponential growth or decay, which again, our model could not quickly account for.
All right, so next, problem 2 asked us to predict whether an individual worker whose job is remote ready will be allowed to and will choose to work from home. To do so, we made 3 assumptions. First, the probability of being permitted to work from home is only dependent on the worker's industry. While we acknowledge that in reality, a person's role in their industry may be highly correlated with their demographics, we overlook this as not to overcomplicate the model. Second, the probability of wanting to work from home rests entirely on these 6 attributes. We believe that these traits cover most of the relevant conditions that might correlate with one's desire to work from home. And finally, we chose to weight the 6 factors unequally, as 2 of them, having children and commute time, are reported to be by far the most significant reasons to prefer working from home. Next, to determine whether an employee would be permitted to work from home, we divided the probability of any employer in the industry working from home in 2020 by the proportion of jobs in their industry that were remote ready. This works because in 2020, the main factor affecting working from home was company permission. Employee desires were largely overridden due to COVID-19. Thus, this calculation gives us the probability that one is permitted to work from home given that their job is remote ready.
When computing the probability that one would choose to work from home, we use this data on a variety of demographic factors such as age, income, commute time, and more from Ipsos and the World Economic Forum. As you can see in the previous slide, we had probabilities that someone would choose to work at home based off individual demographic factors. However, we need to figure out the probability that someone with an array of different demographic factors would want to work from home. Our first attempt was by creating a system basically using basic probability identities like what's seen at the bottom. However, this does not work successfully because you do not get enough linearly independent equations. For the case of two conditions, you get something like the matrix on the right, which is not linearly independent. And in fact, in a pure math sense, this is an unsolvable problem. For example, you can't distinguish between two cases like these on the right. They have a lot of similarities, but not in the intersections. So the solution we ended up picking was a weighted average. And we did this because even though pure math, you can't exactly determine these intersections, in the real world, you'd expect them to be somewhat correlated with the single condition probabilities. So we have this equation down here where we summed the probabilities of someone wanting to work remotely given a condition times a weight. And we gave double the weight to commute time and having children because those were reported to be the highest influencers of whether or not someone wanted to work from home. This has some advantages and disadvantages. On the positive side, it's very dynamic. We can easily add more conditions or adjust it to better data. However, on the downside, it's not accurate for specific types of people. For example, someone with many traits that would make them more likely to want to work remotely, our model may underestimate the probability of them truly wanting to work remotely, and vice versa for others. However, for people with a good mix, it's quite accurate, we found. So our final model, given an individual's demographic data, we were able to compute a weighted average to arrive at the probability they would choose to go remote if given the option. Furthermore, given the industry within which the individual works, we could retrieve the approximate probability they would be allowed to work from home, work remotely from the data. We then made the simplification of assuming that the events of someone being allowed to and wanting to work remotely were independent, which allowed us to multiply the probabilities to get the probability that they would actually work from home. So because of the large variety of demographic and other traits someone could have, we tested our model on 3 example people. I'll read the first one. So a 45-year-old male that works in government, has a medium household income, and is a well-educated parent with a 15-minute commute time, has a 66% chance of being allowed to work from home, a 61% chance to want to work from home, and a 40% chance of actually working from home in the end. Similarly, for the sensitivity analysis, we did it on 3 example people. So we tested how the weights and the average affected the probability they would want to work from home. And you'll notice that the parent and commute coefficients have the highest effect on it by percentage. And we feel this is likely because those were given the highest weight. And we feel like a good way to improve this model potentially would be working on getting more accurate computations of those. The consequence of this model is that there are a large number of assumptions. So for example, the weighted averages we computed may not accurately represent the true probability of someone wanting to work remotely. And the industry, determining the probability of someone being allowed to work from home just by industry category overlooks the large variety of different jobs in an industry, some of which may be easier to do remotely.
Moving on to question 3. For this question, we were asked to estimate for a given city the fraction of workers within that city who will actually work remotely in 2024 and 2027, as well as rank the cities in order of the expected impact that remote work will have on them. We made 4 assumptions, which we will mostly incorporate into our model explanation. So I'd just like to draw your attention to assumption number 2, which is that the set of occupations which can theoretically be done remotely will not change significantly in the next 5 years. We made the same exact assumption in solving question 1, and it ended up being integral to our model. So to model the adoption of remote work, we decided to use the Bass diffusion model. The Bass diffusion model was developed by Frank Bass in the late 60s and is used to model the adoption of new products or technologies. It is defined using the following ordinary differential equation, where the change in the installed base fraction of the product in the population, the product in this case being remote work, divided by 1 minus the installed base fraction, is equal to the coefficient of innovation plus the coefficient of imitation times the installed base fraction. However, this model was not perfectly suited to our purposes because it fails to account for the effects of the pandemic. Factors such as lockdowns and the desire of individuals to avoid contracting COVID at work may have resulted in additional incentives to go remote, which we would not expect to be in place post-pandemic. For this reason, we decided to adapt the Bass diffusion model by replacing the constant coefficient of innovation P with a logistic curve P as a function of time, where P of T is equal to P final divided by 1 plus e to the negative k times T minus alpha, where alpha is the expected length for the remainder of the pandemic, k is the rate of transition out of pandemic conditions, and P final is the maximum coefficient of innovation. Our decision to modify the coefficient of innovation in particular was motivated by the assumption that innovations related to remote work, for example, improved video conferencing software, would likely decelerate post-pandemic due to a decrease in consumer demand. So here we can see a side-by-side comparison of the two models. Our modified Bass diffusion model, shown on the right, has a less steep initial slope. Similarly, it takes longer to reach the same quantity of new adopters. So for the constants P final and Q, we decided to substitute the typical values of 0.03 and 0.38 respectively, as derived from a 1995 study by Frank Bass and others. For alpha, we made the assumption that the pandemic would last for 1 more year, and we set k equal to 2. These last two constants were extrapolated from a survey of disease experts.
In terms of the implementation of this model, we use 2 sets of data. Firstly, the number of workers who were employed remotely in each industry of each city in 2020, and secondly, the theoretical maximum number of people who could have been working remotely in those industries. By dividing this first set of values by the second set, we were able to get the base fraction f of 0 for each industry. We then solved the modified Bass diffusion model for each value of f of 0 to get the future fraction of remote workable jobs that will actually be remote in each industry. Finally, we multiplied these fractions by the projected total number of remote workable jobs in 2024 and 2027, which we solved for in question 1, and summed up the products to get the total number of remote workers expected in each city for the given years. Using this method, we were able to find both the expected fraction of remote workers in the given cities as well as the expected total number of workers. As you can see from our results, Barrie, Wales would have the greatest fraction of remote workers, while Seattle would have the greatest total number of remote workers, and this is due to its large population. However, the question asked us to calculate the overall impact of remote work, and for this reason, we decided to weight our results, taking into account other factors that are specific to the cities.
So the factors that we chose to weight by were each city's average commute time and the percentage of children in its population, because according to a survey conducted by Digital, the well-being of remote workers is significantly improved by having the flexibility to care for their children and by saving commute time. So as for the weighting system, we decided on simple multiplication as we weren't concerned with creating an absolute measure, but rather one that compared the cities relative to one another. On the right, you can see 2 example calculations for the commute factor. We multiplied average commute time in minutes with the percent of workers predicted to be remote in 2027 to get raw values, which we then scaled from 0 to 1. Similar calculations were done for the children factor. So finally, we added up the scaled values to get the final impact scores. Seattle ranked first, and Scranton and Barrie tied for last. This sensitivity analysis regards the Bass diffusion model. Though no constant appears to greatly influence our projections, the results are the most sensitive to the coefficient of imitation Q and the length of the pandemic, alpha. We see great room for improvement by calculating more accurate values for these constants, especially alpha, for which there's the least certainty. As for our final ranking, we would have liked to more completely develop our definition of impact. Our weighting system focuses only on individualistic benefits and could be improved by considering broader effects such as climate change. However, certain fields such as sociology may find our human-centric method of impact ranking more appropriate. Thank you all for your time, and we look forward to hearing your comments.
Okay. Is the mic on? You can hear me? All right. Okay. So thank you for your presentation. My question is going to be about your results for the first question. So for that one, Barrie, which is a rural city, had a higher proportion of remote-ready jobs than Seattle, right, which is a big industrial city. Were you surprised by those results, and can you explain why that happened?
Yeah, I think we were kind of surprised because, Seattle has so many tech jobs and we were expecting those to have a high probability of being remote workable. But we've ended up finding that although Barrie is a very rural area, a lot of the people are actually able to work remotely.
It's also sort of a good point what you said about industry. It is maybe possible that the industrial jobs in Seattle, which most likely cannot be done remotely, may have outweighed in part maybe more of the service jobs in Barrie. We don't really know for sure.
Okay. Thanks. Do you want to ask one, Kelly?
Thank you. Thank you for the presentation. I do have a question on the model 2. You had the probability for working from home. You took the probability that they be committed and the probability that they want to multiply them. Could you comment on why you